Yep, thank you so much for giving me the opportunity to speak. This has been a really great workshop. I'm going to be talking about some topics that are very similar to what's been discussed by previous speakers, but in the offshore domain instead of the onshore domain. And we'll potentially see some interdisciplinary connections that may be of interest to people. So I just wanted to say, first of all, that this work is a collaboration not only with us here in the Caltech Seismo Lab, but also a group at the University of Alcalá in Spain, which developed the interrogator that we use, and also with Marlinks, an industry partner that's interested in submarine cable monitoring and services. So just in the last few years, even though of course DAS has been around for quite a while, more than a decade really now in industry, the applications of DAS in the offshore have really only emerged, at least in the academic side of things, in the last few years. And there were a number of studies kind of illustrating this. It came out in 2019, and there's really been an explosion in the literature since. The idea being that the globe at many different scales is traversed by submarine fibers, either for telecommunications or for monitoring along pipelines or for power cables. And those fibers are sometimes transoceanic and therefore quite sparse, but cover very large distances. Or in the case of like wind farms offshore, they can be extremely dense networks, even though they cover only short distances. And the potential of these was first kind of realized with the interest of expanding the global earthquake monitoring network's coverage, because there's very few seismometers, permanent seismometers at least, in the ocean basins. But it quickly has become very clear that there's a lot of applications related to hazard analysis and applications in engineering that are complementary and very straightforward to apply. One of the big motivations, of course, in offshore engineering and offshore energy development is the need for structural design and foundation design. Depending on the water depth, depending on the local geology and geomorphology, there are a lot of parameters that need to be measured in order to do a good job in choosing a site for your wind turbine or your offshore drilling platform, and determining what sort of foundation you need, and then of course the whole installation process. And this can be quite expensive to measure in situ parameters like shear modulus or shear strength. You need to do either some sort of geotechnical coring using a quite expensive apparatus, or you could do some sort of multi-channel analysis of surface waves to get a VS profile, but that also then requires a ocean bottom source and an ocean bottom array of hydrophones. And distributed acoustic sensing using cables that are already installed at the seafloor or can be easily installed at the seafloor temporarily seems like a relatively natural improvement in these methods because it dramatically decreases the kind of logistical complexity and associated cost for these surveys. And so I'll be looking at particularly mostly data from 1 hour from a really early experiment that we did with Marlinks on a cable that's a primary power cable for the Belwind wind farm, which is one of the many wind farm suites in the southern North Sea in very shallow water. It's about 40 meters water offshore Belgium. And just for reference, this cable is 42 kilometers long. And we interrogated it with a chirp pulse interrogator unit, so Phi OTDR, that was built by the University of Alcalá at 10 meter spacing and 10 meter gauge length. And this is a buried cable. And we observed all sorts of interesting signals. And if you look at the raw passive data in the time domain, you can see that it's extraordinarily complex. You know, here's just 10 seconds over a couple kilometers, and you can see waves moving in multiple directions with all different velocities. And so a straightforward approach to organize this, which is facilitated by distributed acoustic sensing because it's a spatially continuous measurement, is doing a 2D Fourier transform to directly convert distance and time data set into a frequency and wave number spectrum, which allows us to separate waves by their characteristic velocities. And so you can see on the right that this messy wave field on the left has turned into a very clear spectrum with ocean waves going around 10 meters per second on one side that are pushing down on the cable from the surface, and seismic waves, mostly surface wave phases, closer to 100 to 1 kilometer per second at higher frequencies. And it's becoming increasingly popular in, an onshore surface wave analysis to not just strictly apply techniques to the passive data set like MASW as it was originally envisioned by Park, but to apply ambient noise interferometry first, the principle being that you can cross-correlate wave field measurements at 2 discrete locations and extract something that approximates the elastic Green's function between them. And therefore, you can kind of organize the wave field, rendering it much more simply suited to separating different phases and making velocity measurements. And so if we apply that to this data set, by cross-correlating one channel here at 35 kilometers with a broad swath of channels across 30 to 40 kilometers on this cable, you can see very clearly that we get something kind of simulating an active source shock. But there are 2 different wave phases. One is the one that we expect, the Scholte wave phase, which is the offshore equivalent of Rayleigh waves. So this is the kind of surface waves you're going to use for VS analysis. And we also see this really slow phase, which is these ocean waves appearing at low frequencies that have kind of been separated out by the cross-correlation. And as I'll come back to at the end of the presentation, these are also potentially useful for engineering applications, though you might not imagine it at first. So I'm going to briefly touch on 4 different topics. The first 2 are kind of our conventional thought to be in the domain of engineering applications. First, shear wave velocity characterization of shallow sediments, and second, infrastructure health monitoring. And then I'll return to those ocean wave phases and see how they might be useful for our survey. So even though we only have 1 hour, here's an example, quote unquote, virtual source gather, cross-correlating one channel with many channels, zoomed into the surface wave phase. And you can see that we actually have, I've only marked 2 of them, but there are actually 3 different modes of Scholte waves propagating across the array. There's a very weak fundamental mode down here at very low frequencies. There's a much stronger first overtone. And then if you see, there's also some really high frequency striping here that's really barely above the noise level, but that represents a second overtone that you can see in some locations along the cable. And we can just apply standard dispersion curve measurement with a beam forming or a tau p transform. And it's a little messy because of the low SNR, but we can extract multimodal picks. And for the case of this just demonstration, we applied a very simple assumption of a power law velocity profile, which in many marine applications is actually not a poor approximation because the shear wave velocity gradient in the shallow subsurface is dominated by the increasing confining pressure of these otherwise unconsolidated sediments. And we recover a velocity profile along this cable. The cable traverses a couple interesting features. It goes across on the far left, it goes across a shipping channel, which was cut for the port of Rotterdam. And then as it comes off the continental slope into slightly deeper water, still very shallow though, there's several really large tidal sandbanks with many small dunes on top of them. And in between those, it's incised down into a lower Eocene clay layer. So we have some contrast between sand and clay. And we can see these in our very simple model data set. If we plot VS30 as a useful metric, we can see the decreasing velocity with distance as the shallowest, as the shelf thicker, more consolidated sands pinch out. And then here, as we see the incision in between these sandbanks into the deeper Eocene clays, we can see some velocity anomalies associated with them. Though there is an interesting challenge here, which is that these tidal sand dunes are extraordinarily rough. They have active ripples on top of them with a wavelength of about 20 meters. You can kind of see in the bathymetry here. And as we go across those, we basically lose coherence of the measurement. We can still extract some kind of rough estimate, but the uncertainties get large and the scatter of the measurements becomes quite significant. But so that summarizes very simply what we can achieve with just 1 hour of passive data applying conventional shear wave velocity analysis approach. What's interesting is that there are some really unexpected phases in this. Some of the source gathers along the array going through this wind farm not only have this nice direct wave that we're using to measure velocity, but they have all sorts of fascinating funky hyperbola, which are necessarily associated with some sort of secondary source or scatter that's creating a really dominant localized source of Scholte waves. And the natural assumption is that these are wind turbines, and that assumption works out pretty well. So if we reorganize this data set into quote unquote a common offset gather, meaning that we've basically taken pairs of stations that are an equal distance apart and cross-correlated them. So we're looking at the propagation of a wave between two pairs that are equally spaced. Theoretically, then the direct wave is flat. It arrives at the same time everywhere. And so we can subtract it out and observe the complex move out of these localized secondary sources, which we assume are associated with wind turbines. And we can then use that as an input for a imaging algorithm, similar to what's often used with depth and reflection seismology. And what we obtain is basically a map of the probability of where these waves are originating from. And so we can see as we split into some small segments along the array that the segment here in the number 7 is a sea power wind farm, the oldest wind farm offshore Belgium. We can see a very strong persistent source at this I3 turbine. In the Rental wind farm, which was only partially constructed and not fully active during this experiment, we can see a persistent source on this side, and we can see several persistent sources which are hard to distinguish on the opposite side. And kind of amazingly, just with this relatively naive approach and only using a relatively narrow band, this is between about 1 and 4 hertz, we can locate these turbines to within 100 meters, which suggests very strong potential for operational and structural health monitoring, not only because we can see what turbines are active at any time, but because what we're seeing here, these waves generated by turbine vibrations, are essentially the other half of what's typically considered to be called radiation damping in structural dynamics. If you think about forcing a building, it resonates, but it doesn't resonate forever. And of course, there's some friction within the building itself, but a lot of the energy leaks out the bottom. And that's a dominant method of damping by soil structure interaction. And of course, those waves don't just become incoherent energy, they become coherent seismic waves we can observe. And so, for example, different types of surface waves are generated by torsion versus rocking versus shear of the foundation. And so there's a lot of potential here that we haven't developed it yet to quantitatively figure out, for example, the ratio of Scholte to Love waves as a function of the type of motion of the foundation, which could be impactful, for example, in monitoring scour impacting the foundation on an ocean bottom in an offshore wind turbine where that's a concern for structural integrity. So just to, if you're not convinced yet, I just wanted to show it. We have another data set which isn't publicly available yet, and we haven't published yet. But after the Rental wind farm was finished, and after the Northern wind farm was built, because it was not even started at the time of this original acquisition, we went back and collected 24 hours of data. And here's just an equivalent snapshot of a common offset gather where you can associate every single wind turbine here along the closest row in the array with a hyperbola, though reorganized to look more like an arctangent in this data space. So we can really see every individual one, which is quite nice. So, okay, I've talked about the kind of straightforward and maybe less straightforward applications of the seismic phases in passive ocean bottom DAS data sets, but it turns out there's some interesting things to be done with the ocean wave phase. So these ocean wave phases is characteristically slow. It's about 10 meters per second. And so it's actually quite easy to separate it, as you can see, from the seismic waves using ambient noise interferometry. And we can naively just apply the exact same approach that we applied to the seismic waves, basically MASW for ocean waves, to measure the dispersion relation for ocean waves along the array. And this dispersion relation, if we assume that there's nothing fancy going on, no currents, no nonlinear interaction, is primarily most sensitive to the water depth. And that means that we can basically do a surface wave inversion for the ocean wave phase and recover a profile of the water depth along the cable. So what you see here in red is the measured depth from multi-beam along the cable. And you can see in black the inverted depth for this segment from the DAS. And we have a systematic offset. Clearly something is slightly wrong in the model we're using. It's about 8 meter systematic offset. But we've clearly recovered this shipping channel cut for the Port of Rotterdam. We can see the slope. We can see the 2 sand banks out here. It's really quite an impressive ability. And so there's 2 aspects of this that are valuable. One is, of course, if you're interested in monitoring changes in sedimentation, which could be related to scour in the case of wind turbines and offshore structures, or related to cable burial in the case of attempting to monitor the state of health of a cable that you're trying to protect from the human activities like trawling that could damage it. You of course want to be able to monitor the bathymetry profile in time along your cable, but also there's a question of geometric co-registration. In DAS, we have optical distance that we measure with the interrogator, and then we have the physical distance of the fiber we lay out. Jonathan mentioned using tap testing with active source hammers on land to co-locate your optical distance with your cable position, but offshore you can't necessarily do that because it's at the ocean bottom. But where you have interesting bathymetry features like this ridge, you can measure the bathymetry using your profile and using your cable and utilize that to co-register the bathymetry. And just finally, wrapping up, there's actually a lot of potential insight into marine hydrodynamics, which may be of interest. We've talked about characterizing VS and some infrastructure monitoring that may be useful for foundation design, site selection, site amplification, and PSHA. But also, of course, if in this kind of holistic offshore engineering framework, you're also interested in constraining wave and current loading of structures, which can be quite hard to measure in situ without a dedicated buoy. And you're also interested in the kinds of currents that are involved in scour and changing sedimentation that could impact your structural health in the long term. And it turns out that DAS is really pretty sensitive to not only the amplitude of the waves, which could be calibrated to be related to quantitative metrics like significant wave height, but also the dispersion relation of the waves, which is non-reciprocal. So we can actually see in this offshore Belgium data set just over this 1 hour that in this FK spectrum, so this is the, again, frequency versus wave number, waves propagating in one direction towards the shore are moving faster than waves propagating in the other direction towards the ocean, meaning that there's basically a Doppler shift. The waves are propagating in a current. And so using, again, kind of an adaptation of methods from seismic tomography, we can look at the change in the travel time of ocean waves as a function of many different hours. This is a 24-hour data set from 2019. We can measure then a current speed and map this along the array. And we can see, as expected, the current speed is higher in shallow water just because of conservation of mass. And as we hit these really large sandbanks, we get a phase shift because the current is pushing against them at an oblique angle. We can also see, of course, that this current in Belgium is dominated by the M2 tidal component, as you expect for currents most places. So that, of course, would be very useful if you're interested in scour modeling, because you don't have to just rely on an a priori assumption about the currents in your locale. You can use an in situ measurement. And so just to wrap up, here are the conclusions that I've all talked through already. But here's just an example of the generalizability. These yellow lines are all and red lines are all individual cables that contain fiber optic elements in this wind farm locale offshore Belgium. And you can see that there's already basically the groundwork for a dense passive monitoring network, both inside and outside of these turbines and in the surrounding sediment, running through areas where there might also be, for example, future development, because this wind farm here in Northern was actually built after these. So they were pre-existing cables running through its allocation before any turbines were installed. So in conclusion, I just want to point you to some resources on ocean bottom DAS to get going, both our work. If you'd like a preprint of this work at the end that's not published, just email me. A lot of interesting work from the group at Rice and some groups in Europe and Japan on further applications down this direction. And also just an FYI that you can get this data set, the first 1 hour data set from 2018 online for free.
Excellent presentation, Ethan. Thank you very much for sharing this. And there's really a lot of interesting stuff in there for people to consider, I think. And so we'll definitely be in touch.
Thank you.
More in the future. So thank you. Our next speaker is Joseph Van Tassel. Joe is here in person. Joe is a PhD student at the University of Texas. Will be defending his dissertation within a few weeks, actually. And currently he's working for the Texas Advanced Computing Center, TAC, on high performance computing and helping people with large data sets. So I'll turn the time over to Joe to begin the presentation. Joe here.
Great. Well, thank you for the introduction. It'll save me a bit of time. I have a few slides I want to get through here. Today, we'll be talking about extracting high-resolution, multi-mode dispersion data using MASW on the ground surface at a site in Austin, Texas. And I'm waiting for the slides to change, hopefully. There we go. Okay, so this is the site at Hornsby Bend. You've heard a few people talk about this in various presentations. At this site, we have 200 meters of fiber shown there in that solid orange line. And then adjacent to that, we deployed 94 meters of geophones in order to be able to make comparisons between the waveforms that we're getting from DAS and the waveforms we're getting from the geophones themselves. To do our MASW, we used active sources. So we used several different of the trucks here at NHERI at UTexas, as well as some impact sources, and I'll talk about that in a little bit more detail. We used a variety of locations. We'll only be talking about 4 of them here, and those are denoted as their distances from the first geophone, so -5 meters to -40 meters. And then to be able to make comparisons to some ground truth, we're going to make comparisons to 3 CPTU measurements that were made at the ends and at the middle of the geophone line. So a little bit about the DAS installation. We actually installed 2 different DAS cables. One is the NANZ strain sensing cable, and the other one is an AFL tactical tightly buffered cable. For the presentation, we're only going to be talking about results from the NANZ, and we're going to leave the AFL to later, and I won't be talking about that today. To install the cable, we buried it into a shallow trench. I have the 2 arrows there in the top right, which are showing that there are indeed 2 cables there. It's kind of hard to tell from the picture. And we put those adjacent to one another in the trench. And then the NHERI at UTexas crew buried these, making sure that they were straight and they're buried appropriately. And then the ends we brought up and placed in these junction boxes so that we can make clean connections to them. And it's also important to point out that these cables are sensing inline. So they're sensing wave propagation that's inline, horizontally inline. And that'll be important when we make comparisons to the geophones. The interrogator that we use is the OptiSense ODH4. We're using a 2-meter gauge length, which is important when we're doing near surface testing like this. And we're using a 1-meter trace separation. The sensing is proportional to strain. And so that'll be also important when we make comparisons to the geophones, which are sensing proportional to velocity. In terms of post-processing of the results, we were downsampled from our ping rate, which was 100 kilohertz, down to 1,000 hertz to do our processing. And then we applied a 3 hertz high-pass filter to those waveforms to remove any DC artifacts. The geophone array that we deployed alongside the cable, the geophones were GS11D, and they're 4.5 hertz phones from Geospace. We deployed both vertical and horizontal geophones. And so you can see those are mounted in those land cases, and they're put alongside this disturbed earth here is where those cables are buried. And you can see that the vertical and the horizontal are sitting right next to each other. The horizontals are oriented in line because, again, that's what the DAS is sensing in. And so we want to be able to make direct comparisons there. We'll only be talking about the horizontal in this presentation, and we won't be skipping over the vertical component. The way these are coupled to the ground surface is with a 3-inch spike. And so you can kind of see when we put them out on a table, you can see this 3-inch aluminum spike, and we push those into the ground. So the sensors are not buried, but they are well coupled. As I mentioned previously, they're sensing proportional to velocity. And then finally, the only post-processing we need to do is to take the physical measurements we have, and we need to remove the sensors' frequency-dependent amplitude and phase response. And so we did that in this case. As I mentioned, we used a variety of different sources at Hornsby Bend. So we had T-Rex, and we were shaking using all 3 of its principal axes there. We'll only be talking about the vertical, the P mode, so to speak, and then the inline, the SL. We won't be talking about any of the cross-line shaking that we did. We were using 12-second chirps that go between 3 and 80 hertz. So we're getting a pretty broad band spectrum there. Then this, of course, as people have previously mentioned, T-Rex has got the highest force output of what we're looking at here. The next step down from that in terms of force output is thumper. What thumper allows us to do is shake to higher frequencies. So rather than going up to 80 hertz, now we're able to push that up to 200 hertz. And for this deployment, we were only using thumper in its vertical mode. And then finally, we have a sledgehammer source, which we don't have as much control over the frequency content and obviously a much lower force output. But as that can be very practical for these types of things, we use that sledgehammer source as well. So I want to talk a little bit about the waveforms before we get into the MASW results. So here what we're showing is things in terms of displacement. And I want to show things also in terms of velocity here in a second. To talk a little bit about how we went and got these into units of displacement. For the DAS, we need to first convert the raw data that's in the units of phase change to strain using the equation that's shown here. And then we multiply by the gauge length to get our displacements. For the geophones, we take the initial units, which are in counts, we remove that frequency response that get us into units of velocity, and then we integrate to go from velocity into physical units of displacement. And then a comparison, so what we're showing here on the left in blue are the geophones, and for this case, we're showing a shot from T-Rex, or we're actually showing 3 shots here with T-Rex. So the width of the lines that you're seeing is the 3 different shots that we did. And so you can kind of get a sense for the amount of noise we had between those shots based on the thickness, more or less, of those lines. And the same thing with the DAS here. The DAS is being shown in that brownish color. If we make a comparison in terms of velocity, we're going to do a very similar processing procedure, except now for the DAS, we need to differentiate that displacement into a velocity, and then we can skip the integration that we did for the geophones, as those are already sensing in terms of velocity, and that's what's shown here on the right. And so I can just show these side by side now to just show that we're getting extremely good agreement in terms of the phases. The cycles are lining up. We're seeing similar things between the displacement, the velocity, and between the geophone and the DAS. But what we're having a little bit of differences in terms of amplitude. And so part of this is a gauge length effect, and part of this is, of course, coupling and other factors that need to be further investigated. But the good thing is for MASW, really what we care about is the phase of these. To show a slightly different comparison, this is with the sledgehammer. So the sledgehammer, as I mentioned, has a much lower force output. So we have a much lower signal to noise ratio. And so what you can see is as we go further along the line, this is geophone 0 up here at the top and geophone at 94 meters. And if we look over here at the velocity, because these blue lines, which again are the geophone data, it can be quite noisy at those further offsets. But what you're seeing is that partially due to being buried and its increased sensitivity, the DAS is not picking up as much of that noise as the geophones are. So we're seeing really good signal all the way out to 94 meters, and we actually can even see signal much further. And this is just from a sledgehammer impact. And you can see, of course, that when we go to make comparisons in terms of displacement, that integration we need to do on the geophones is just amplifying that noisy measurement that we have. But you can see that there's some coherent signal that we're able to perceive from the DAS measurements, which is a really good sign. So before we talk about the actual MASW results, I want to do like a brief overview of dispersion processing and what's involved in it. So we start by having a linear array of receivers, and that's what's shown with these black triangles. And then we have a source here shown in this blue diamond. And what we'll do is we'll record waveforms that have strong Rayleigh wave content. So we'll activate that source, and then of course that wave is going to propagate with time down the array. And so of course that wave is going to go and propagate down like this. So here we can clearly see surface wave energy. We then beamform those signals. So these equations are representing up here at the top to be able to extract phase velocity, which is the vertical axis here, as a function of frequency. And so once we make those picks on this phase velocity frequency plot, we're able to get a measurement of our dispersion. So now the question becomes, well, what effect is there if I process in displacement versus raw units versus velocity? And the good news is that if you use frequency dependent normalization, there is essentially no difference between whether you use the raw phase change in radians out of the DAS, the displacement, or the velocity. And you can see in this case, with this T-Rex shot at -40 meters, we are recovering high quality fundamental and first higher Rayleigh wave modes of propagation. And there is also other higher modes that are a little bit harder to identify, I should say, but they are clearly there. And so now this is all of the results. So we're showing 4 different offsets, and we're showing 4 different the sources. So we have quite a few different ways of estimating dispersion at our site. And as a result, there are some scatter in the data. However, we can clearly see that we have 3 fundamental and 2 higher mode Rayleigh wave dispersion curves, which but before we talk about that, there's one thing I want to point out, which is the effective gauge length. So you can see we have similar dispersion in the 3 modes, except at high frequencies. And if you recall, we're using a 2-meter gauge length here, and it turns out that right around here is about a 2-meter wave, a 2-meter wavelength. And so what you're seeing is an inability of the DAS to really extract that high frequency dispersion data. And so now what we can do, we can trim out that data and isolate those modes. And we can see again that we have those 3 clear modes. But of course, what we want to do here is make a comparison between the DAS measurements and the geophone measurements, which is what is shown here. And so you're seeing we're getting the same Rayleigh wave dispersion data up to the 2nd higher mode from both the geophones and the DAS. And again, it's even clearer now that gauge length effect I mentioned, where the geophones are able to recover much higher frequencies. So now we want to go beyond extracting the dispersion data itself and actually go to the inversion process. So what we're going to do is only present the fundamental Rayleigh wave inversion. You can of course invert for all 3 of those modes or any subset of them. We're going to use the uncertainty consistent procedure we published earlier this year. We'll be using 4 different layering parameterizations. So 4 different assumptions about the number of subsurface layers, as we don't know that in advance. Using the uncertainty consistent procedure, we need to do a different number of realizations, for which we're going to do 250 per parameterization. So 1,000 of these inversions in total. We'll be using a global search algorithm. And for each of these 1,000, we'll be searching 70,000 trial models to find the best fit to that realization. So we're searching over 70 million models here. And of course, we're going to be doing that twice, once for the geophone and once for the DAS. And end result, after we follow through that uncertainty consistent procedure, here what we're showing is 1,000 theoretical dispersion curves, which are associated with our shear wave velocity models that I'll show in a second. And what we're showing is that these are representative of not only the mean, but also the standard deviation at each frequency that we were able to recover, the left, of course, being the DAS and the right being the geophones. And here are 1,000 shear wave velocity profiles on the left, again, the DAS, and on the right, the geophones. And I want to point out that we can get these 1,000 shear wave velocity profiles, we can get a median profile, and then we can also estimate shear wave velocity uncertainty. It's a function of depth. And of course, because we're only using part of the data we extracted, these are going to be conservative estimates of uncertainty for the site. And of course, we can compare those between the geophones and the DAS, and we see consistent estimates of shear wave velocity as well as the uncertainty that we get from both. And if you remember, we had 3 CPTU measurements at our site, which we can then correlate to shear wave velocity. And so what we're showing, the 3 different CPTs are shown in different colors here. And we're able to estimate a median and standard deviation by using different CPT to VS correlations. We are just using 3 here, 2 from Andrus and 1 from Robertson. And so what this is showing is that the MASW measurements that we're able to get is giving us reasonably consistent shear wave velocity as we would get from invasive testing, and a similar uncertainty as well. And with that, I'd like to acknowledge the funding that supported my time on this, on the National Science Foundation, as well as the computational support from the Design Safe Cyber Infrastructure and the Texas Advanced Computing Center. And so with that, I have a summary slide, but I will not go through the time to read it. Thank you all.
Perfectly on time. Thank you, Joe, for your presentation. Our next speaker is Dr. Eileen Martin. And Eileen is in the middle of transitioning now from Virginia Tech to Colorado School of Mines. And so Eileen will be speaking to us today about data science approaches in DAS. Essentially, how do we handle these massive data sets, which is a super important topic. So I'll turn the time over to Dr.
All right, thanks very much. And thanks for letting me join remotely. That made it a lot easier to participate today. So yeah, I'm going to give kind of a bird's eye view of data science approaches to working with DAS data. As many of the speakers previously have mentioned, these experiments often have multiple terabytes of data per day, a lot more than we're used to working for, especially for engineering or near surface or infrastructure applications. So some of the applications that are inspiring these methods include things like urban seismology, where we're looking at earthquake hazards or making sure that infrastructure is going to be safe, studying glacier movement or ice quakes, doing permafrost thaw studies in areas where that's threatening our infrastructure, and also for subsurface energy exploration and monitoring. So just to put that in context, those are the applications that have specifically motivated my work and my group's work in this space. So to give you a feel of sort of typical data rates and quantities, if you haven't done experiments yourself with DAS, we're typically looking at things like millions of points per second or more. That is to say, many millions of points per second that are number of sensor channels in your DAS array times the number of samples per second. And there are a variety of different experiments that we've summarized this for, just so that we could get a sense of like if we can have long-term experiments with low data rates, maybe repeat experiments with very high data rates, and all range in between. And just taking a collection of 9 of those experiments, we can see that these vary a lot in their cumulative data rates. But just like these 9 experiments that were done by academic and national lab groups have added up to more than 800 terabytes worth of data from just a few groups. And so that tells you just what we're up against when we're thinking about how could this fit into the world where we're expected to make these data public. And comparing this to the IRIS Data Management Center that's often used in the seismology community for sharing archive data, that's roughly the same amount of data. Actually slightly more data than the entire IRIS DMC over the past couple of decades. And so this is going to take a huge investment in cyber infrastructure to be able to actually support these data openly where people can request them. And it may even take some changes in how we think about how we share our data. Are they full resolution or compressed? Are we always able to get them? Or are there only certain time periods where we can get them? Or are there different levels or tiers of how we're able to access those data? And I work a lot on passive seismic data. And so the types of analysis that we need are things like being able to do data exploration and quality control. Being able to analyze our noise is really critical to being able to use it as either a source of energy or to take it out if we need to use the rest of our signals. We need to be able to do weak event detection, and we need to be able to do things like passive ambient noise imaging, which was brought up by a couple of the speakers previously. So, like I mentioned, we need to be able to characterize our noise or remove our energy, or to use it or remove that energy if we want to use other parts of the signal. So here's some examples of some energy that was collected, just like 10 seconds worth of data at the Stanford DAS array. And here's a week's worth of signal. And we see a lot of changes day to night, and in different locations, even within the same experiment, we get very different spectra for our responses. Here's an example of an experiment that was run by Lawrence Berkeley Lab that has very different noise as well. Here's an example of pedestrians walking throughout the Penn State array, which was something we didn't see in other experiments. Here's an example of some floats and motorcycles that were seen by Caltech in their experiments. So we have these very different types of noises in different cities around different types of infrastructure. And it would be completely infeasible to have someone sit there and manually label all of these data. So we have to turn to other kinds of approaches, for instance, unsupervised learning or clustering, for instance, to start to organize our data so that we can then target what are we spending time on manually interpreting and understanding. So I got a chance to work with Farn-Yuh and several others at Stanford when we were running the experiment there. And one of our issues was that we wanted to get rid of cars that were detected. And we had tried to do physics motivated methods of doing this before, but it just wasn't quite there. And we knew that this showed up in all of the urban DAS experiments, so it was important to do. And so we were able to design some features. For instance, things like the continuous wavelet transform were really successful in being able to separate out different clusters. And so we ended up using k-means clustering, and just a few clusters were able to pretty robustly identify vehicles from different parts of the array. And we could verify that against what are the times when people are driving, where do we expect them to be driving, those sorts of things. And so we could separate out, for instance, cars in one cluster from other loud noises in another cluster. And we were able to get things like what are the typical move outs of those cars, things like that. One of the great things about DAS compared to, say, individual seismometers is that we're able to do these kinds of continuous wavelet transforms, not just in time, but in space as well. And so this gives us more flexibility on the types of features that we can then feed into various machine learning methods. When we went over and started up the Penn State First C array, which is a couple of kilometers under the Penn State campus, we had totally different kinds of noises. It turned out it was actually quite a bit more sensitive than the Stanford array. We could see, for instance, footsteps in a pedestrian area. We also saw things like audio signals that we thought could not be supported because we hadn't seen airwave signals previously. And so that was pretty exciting. But it told us that, not every college campus even is the same when you're recording these data. So we really do need these more automated tools. One thing that we saw there, though, was those footsteps, and we were kind of concerned because there is this goal of having more ubiquitous seismic monitoring for, say, earthquake hazard analysis and early earthquake warning and things like that in urban areas where maybe people won't be that comfortable with having their footsteps recorded. On a college campus, it's fine, but in a mixed residential and commercial neighborhood in a city, maybe the residents won't want to have their footsteps detected. And so I worked with a team of undergraduates in our computational modeling and data analytics program to put together a deep learning solution where they actually created a database of a couple of thousand windows of data, labeled them as having footsteps or not, and we were able to train a convolutional neural network just on our data with a little bit of processing on it so that we could actually get pretty good accuracy in the 85 percentile-ish range for being able to detect these footsteps so that we could then randomly remove them from the data so that people might be more comfortable with having these kinds of data recorded where they live and work. Another example where we were running into these issues of having a wide variety of noises was on Rona Glacier, on an experiment that was led by my collaborators Fabian Walter and Andres Fichtner. And this was about 10 kilometers worth of fiber optic cable deployed over this glacier that has tons of melt streams, ice quakes going on, lots of wind. We even see signals from a sunrise and sunset every day. These kinds of things really affect our data, and they make it really hard to manually go through and understand what's there. So I worked with Julius Grimm, a master's student on this project, where we actually were able to process our data and come up with, again, these dense array-based features, things like our tau p transforms, looking at sort of a simplified low rank or low dimensional version of our slownesses, as well as things like array coherency and the eigenvectors and eigenvalues of those array coherency matrices to be able to do unsupervised clustering of our events. And so we were able to label different windows of data in space and time as having these different types of ice quake events of various categories. And our different clusters showed us these different categories of events that we're now using to be able to understand more about what are these different categories of ice quakes that are going on, why are they distinguished from each other in separate clusters, and what can they tell us about how the glacier is behaving in different areas and different periods of time. And cluster 0 here, I'll point out, is just our noise cluster. So going back here to where we had different time and space locations labeled, all of the white is where it's just sort of quiet background noise, no identified events. So we can start to see these kind of repeating events that are sort of scattered partway through, and some other events that we're still trying to understand. But one of the big things that we found with that project was, especially to support an international collaboration, where we needed to be able to have common space for compute access and sharing data, and we didn't have a public repository that could support the data quantities that we had. We actually had to turn to cloud tools, and we weren't the first ones to do this. So the DOE's geothermal data repository has a lot of public DAS data up already on Amazon's S3 cloud services. And so we also bought space on Amazon's S3 services for having our data stored as kind of an archive that we could all commonly access on servers in Central Europe. And then all of us from the US and from Europe are actually doing our compute up there, as well as having the data stored there. And that helps us to avoid a lot of costs and a lot of time waiting for moving our data around, which again, with these DAS data, can add up to a lot of time. And in fact, we've kind of optimized our workflow a bit more to have different levels of speed of access to the data that we're working with. One of the other strategies that we're having to use besides just cloud computing for managing these large data quantities is actually doing more computing in the places where we're actually collecting our data. And so in August, I got to go out to Utqiagvik, Alaska with Ming Zhao and collaborators, where we're doing a study of permafrost thaw there. We don't have a lot of bandwidth, and so two of the students working with me, Samantha Paulus and Brandon Pearl, put together a bunch of codes so that we're able to actually calculate different summary statistics and data products, things like our bin spectrogram, our low frequency downsample data as they're being collected, so that we don't have to go through all of our raw data at first. We can just go and remotely access to get these little data products, which we can then transfer over the small amount of bandwidth we have accessible to us. Then once a month, we get our hard drives with our actual full resolution data so that we can do more advanced imaging from there. But these kinds of edge computing workflows are getting integrated into more experiments. I know, for instance, the teams at Lawrence Berkeley Lab and Rice are also working on these kinds of strategies, which are becoming more and more important. And when we think about what's the role of this in doing machine learning analysis, well, we could be doing all of our feature calculation while we're collecting that, or at least much of it. So it's a new direction that's kind of evolving at this point in time still. The other part of the analysis that I want to talk about is this ambient noise imaging, which is based on essentially estimating virtual source responses, as was mentioned earlier by some of the other speakers, like Ethan Williams was showing this. So we're trying to get some kind of dispersion image after we get sort of a wave equation Green's function response based on cross-correlating a ton of noise. And when we look at a lot of strategies for weak event detection, like template matching, that also boils down to something like a normalized cross-correlation between different time series. And so we've really focused on how do we kind of speed up this process of cross-correlating a bunch of time series. Thinking about our standard ambient noise analysis, if we have N sensors in our DAS array, and we want to do this kind of ambient noise interferometry, it scales like the order of N squared, which is really bad because it also scales like that as far as how much data we have to move around. And so we've actually come up with a variety of strategies for how can we deal with these ambient noise interferometry analyses more quickly. And so one thing we've done is looking at, can we do approximate cross correlations? And especially if we're just working with a bunch of noise from random sources, we might think about, can we do some kind of lossy compression of our data? For instance, low rank cross correlation or wavelet cross correlation, or that we can do our cross correlations in these kinds of compressed domains. So we can store our data in this compressed domain of a low rank approximation or a wavelet compression. And then we do all of our analysis in that same compressed domain without ever decompressing it. And that saves us quite a bit of time. For instance, the low rank approximation for the Stanford fiber optic array helped us save something like a factor of 140 times faster in our analysis. We can also think about not just doing approximate cross correlations, but still calculating the same thing and revisiting our algorithms so that they scale better. For instance, if we just want to calculate our dispersion images to go into our surface wave inversion, we can skip the cross correlations altogether and do them implicitly as part of our dispersion image calculation from that raw seismic noise. And we can do the same thing if we're looking at body waves, trying to do double beamforming from our ambient noise analysis. I think I'm pretty short on time, so I'll have to skip over this last part, but hopefully seeing this kind of outline of solutions gives you some sense of what are some of these fast algorithms out there to reduce our data movement for high throughput DAS data analysis. Here's just some cartoons of how those algorithms work and what our scalability is like, orders of magnitude faster, which is pretty exciting. So just to wrap up, I'll point out that these DAS data, again, are much larger than what we've worked with in the past oftentimes. And we've especially focused on doing things like exploration and labeling of events so that we can use those for either targeted energy for imaging or for removal. And those really benefit from our unsupervised or supervised machine learning methods. We have a variety of options open to us. And for doing ambient noise analysis, we've really been able to focus on reducing our data movement and had orders of magnitude gains in how fast we can analyze these data, which means we don't need necessarily to have a supercomputer running things for an array that only has maybe 1,000 sensors. Or we can scale to many, many more sensors, like tens of thousands of sensors, which is kind of where we're going with DAS now. So I'd like to acknowledge all of the funding for these different experiments and that have supplied data for us to work with. Also many collaborators on this work. And if you're interested in DAS, data analysis with machine learning, I'd encourage you to get in touch with me. We have a DAS and machine learning working group as part of the DAS Research Coordination Network, and we'd love to have more members as part of that, especially people that are part of the engineering community. So thank you very much.